So in this video, I'm going to recap some of the concepts around regression. So all a regression really is using a bunch of different factors to predict another factor. So these ones here that I'm using X for, these are like the independent variables. So these are each going to feed in some information in order to predict another variable, the dependent one, which we're calling Y. So as an example, if I want to predict your height, the dependent variable Y, then maybe some factors that would be useful in predicting it would be, say, your gender, maybe your cultural background, so your race, and then maybe also your mother's height and even like father's height and so on. So you can have as many different factors as you need in order to predict this other variable. So all this is really doing is developing a relationship. So we could write this mathematically as Y equals, and you write it as f being a function. So it's a function of x1, x2, x3, and so on, as many as you'd like to consider. And if we take the simple case where we just have one factor that we're considering, this would be like y equals a function of x. And we're going to be looking at linear relationships here. So we could write this as basically an equation of a line. So it would be mx plus c. Okay, I should write this with a capital X. So this m in here that you're probably familiar with in terms of equation of a line, this is like your gradient. Okay, so depending on what this value is, either your line when you draw it, so if this is y and this is x, if m is positive, then it will be like an upward sloping line, so inferring like a positive relationship or positive association between your two variables. Or if it is a negative value, then it's going to go downwards, so you have a negative association between your variables. So this gradient is quite important in determining the relationship between them. And of course the size matters as well, because it's going to make your line either steeper or shallower. So the other thing that we have here is C, and this is like the Y-intercept. Oh, I spelled that wrong, intercept. Okay, essentially this controls where your line crosses the axis. So if we have a line like this, and we dot it back, this here is our C value, where it crossed over. Alright, so let's pretend now that we have some data that we want to fit our regression to. Okay, so we've got an X and we've got a Y. So if we put in some data, let's pretend we have these points here. What we're going to do is try and fit a line through those as best possible. And what you'll find is as you change the gradient and you change the C value, you're going to get a line that's better or worse. So for example, if I fitted a line like this, that's probably not as good as if I did a second one. Let me pick a different color that went, say, like this. Okay, that one looks a lot closer to my data points than this one does. Okay, and you can actually quantify that if you want to by figuring out the error, which is basically the distance between your actual point and where the line sits. So this here would be the error with regard to the green line. Okay, so it's quite big in some places, and you do it for every single point. So you can quantify this error, and what we get a computer to do is minimize it. So that means that the computer changes the gradient of this line a bunch of different times, and it figures out where the best place is to put it such that that error is minimized. Right? So rather than having all these random attempts, what we end up with is just one attempt, which is the best possible fit for that bit of data. Okay, so you can kind of think of these regression equations as a line of best fit. Right, line of best fit. And usually when we do this for statistics, rather than writing it with this type of equation where we have y equals mx plus c, instead we get out different names for these coefficients. So instead we would call it y equals b0 is the equivalent of c, and then b1 is the equivalent of the m here. Okay, and you can make this go to higher orders, I guess. So for example, this is the equation if you just have the one independent variable x, but say you had more, then it would just become an extension. So BO, again, is just our intercept where it crosses over the axis. All right, and then you would just have a few of these. So you'd have B1x1, B2x2, B3x3, and so on, as many again as you needed in terms of your independent variables. So each variable is going to get associated with one of these kind of gradient values or coefficients. So what we like to do in statistics is test whether these coefficients are actually meaningful, or whether in fact they're not really having an influence over the result. So if we go back to our simple example here, if we ended up finding that the relationship between x and y, say our points look like this, so the line of best fit ended up basically being flat. That means that whatever this x value is or represents isn't really doing much to control our y value, okay? And if you in fact get a flat line, that means that the gradient here is actually equal to 0. Okay, so that would be like the m value if you're using this form of the equation, or if you're using a more statsy approach, it's going to be this b value. Okay, so b would equal, I should write this as b1 since we have a b0, but b1 would be equal to 0 here. So if that's the case, then there's no real relationship between x and y, and this is something that we're going to be interested in testing for. So if we go back to thinking about when we have a population and a sample, scroll down. So if this is my population, what I'm going to do is take out a sample from that population and figure out my regression equation for that sample. Now, the regression equation for the population is something that we're probably not going to know, since you would have to sample the entire population to know it. So technically the equation though would look like this. Again, I'm just going to use one variable here to make it easier. So this is our dependent variable is equal to, we're using the Greek letters here since it's the population. So beta 0, this is just the intercept for it, and beta 1 is the gradient or coefficient associated with our independent variable x, and e is just some error that's on the end. So if we were to try and make a regression equation for our sample, technically we write it like this. So y, our dependent variable, is equal to, this is where we use the lowercase, so b0 plus b1x, plus again we have some error associated with the result. So what we're going to do is take our sample and fit this equation to it, and we should be able to figure out what our b value is, and we're usually interested in the ones associated with the coefficients. So b1, and then if you have more independent variables, 2, 3, 4, 5, and so on, we don't really look at this b0 variable at all. So what we do is more hypothesis testing on this. So our hypothesis would be to see whether this b1 value means anything, is that our null hypothesis would be that b1 for the population is equal to 0, because we saw that if this coefficient was equal to 0, all right, like here, it means that there's really no relationship. X doesn't really contribute to y at all, okay? So I'll put in brackets here, no relationship. And that's why it's the null hypothesis. It's the boring one, it's the one of no change, maintaining the status quo. So H1 becomes our alternate hypothesis. So this is the interesting one, or the one of change. And for this, often what we are testing is that B1 does not equal 0. However, you can look for it in a direction. So you can have B1 is greater than 0 or B1 is less than 0 as well. Okay, so these are our alternate hypotheses, and they are suggesting that a relationship exists. Okay. So these ones are just implying the direction. So if b1 is greater than 0, okay, that means that the gradient here is positive. So we said that positive gradient between x and y meant that it drifted upwards. So this was like a positive association. Exists. And the opposite case here is when b1 is less than 0, that means it's a negative number. So then that case, it would drift downwards in terms of the relationship between the two variables. So that would be that negative association exists. Okay, so they're your three kind of options for the alternate hypothesis. Depending on the situation, you'll pick which one is appropriate. I guess one thing to point out though is that if you do the does not equal 0, 1, that's implying that you're going to test in both directions. So this is a two-tail test. If you do either of these two, these are only testing in one direction. So this would be performing a one-tail test. So otherwise, you follow through the rest of your hypothesis testing procedure really just using Excel. So Excel will calculate for you the p-value, which is the probability of getting the b, or the coefficient for your sample, or something more extreme. And then of course you compare that p-value to your level of significance to decide whether you have enough evidence to accept or reject the null hypothesis. And hopefully you'll see this procedure in action through the example videos, and it will become a little bit more clearer. So I'm going to leave that at that point for now. And the only other thing I want to talk about is how good your fit is for your regression model. So if we scroll back up, let's use this one as an example. All right, so these were our actual points, and this was the line of best fit. So obviously there's some error associated with this, okay, between your actual value and where the prediction actually lies. So there's a way of measuring this, and it's known as the R-squared value. All right, might chuck it over here. So I'm not going to go through the maths of it, but basically this R-squared value adds up the error between your points and the line of best fit, and it will give you a number associated with it. So I'm going to put measures quality of fit here. So there's a range where your R-squared value can sit. So if you get an R-squared of 0, that is like the worst possible fit ever, okay? So that's the bottom limit. If you get an R-squared of 1, I'll put equals 1, probably makes more sense, equals 1. That means that you have an absolutely perfect fit. So that's the best possible. So usually you're going to be sitting in this range in here between 0 and 1. So the closer you are to 1, the better your fit actually is. Alright, so that's pretty much it in terms of what I wanted to cover in this recap video. So hopefully you can get a bit more clarity on these concepts through the examples.